Okay, so I'm giving a crash course on LHC physics. I hope you all got the pun. Crash course, crash course. Let's see, very few of you got the pun. And let me just say a few words by way of context. You know, it's really amazingly exciting that the LHC is turning on this year. For many years, it was a time translationally invariant statement that the LHC is 5 years away. And the fact that that's no longer true is a rather amazing testament to the skills of our experimental colleagues. So it's really turning on this year. It's turning on, probably many of you know this, it's turning on with a center of mass energy of 10 TeV, not the target 14 TeV center of mass energy. And by the end of this year, we'll have accumulated something like 10 inverse picobarns of data. If you don't know what that means now, you'll know what that means by the end of the lecture. So this year is very, very likely not going to be enough energy or data for discovery. But after a winter shutdown, we'll start back up in March or April at the target center of mass energy. And then, for reasons that will become clear by the end of the lecture, discoveries could happen very fast. Okay, this is the whole point of building a machine which goes up in energy by a factor of 7 compared to the highest energies that we've gotten so far at the Tevatron. Discoveries could come very fast. And, but really what's going to happen is that I predict, I think it's sensible to expect, 1 to 2 to 3 years of utter chaos and confusion as rumors come out, as data starts coming out, as people start trying to interpret it. And that 1 to 2 to 3 years of chaos and confusion is going to lead to some picture for what the effective Lagrangian is at or what the effective theory is at the TeV scale. It might take longer than that. I don't think it's likely that it'll take shorter than that. Okay? But that first 3 years is going to be where a lot of the action is, and a lot of the action of the sort that we haven't seen in our subject for 35 years. Now, if you're a string theorist, then all you care about is that TeV scale Lagrangian, if you care about that. But to the extent that you care, you think, oh, I need that TeV scale Lagrangian. And then I will take that theory, and then I will try to figure out how it connects to a bigger theory, the big ultraviolet structure, and so on. So one strategy could be, I'll just go to Tahiti. I'll wait for the experimentalists to figure it all out, settle it all, and then once we have the TeV scale Lagrangian, then we'll come in on our high horse and figure out where it comes from. And you know, that's maybe logically doesn't sound like such a crazy idea, but but it really doesn't make that much sense, because of course the people struggling to figure out what's going on in this period of confusion aren't going to be completely ignoring where this might be coming from themselves. Okay? It's going to be, I think, a very interesting, chaotic, complicated, but hopefully very intense back and forth between experiment, TeV scale model building, and high scale physics. And it'll all be going on simultaneously, I think, almost right from the start. So what I want to do is give you the tools in these lectures, is give you the tools to figure out how to jump into this business and make some, and if not, play an active role in it, which you might want to do. At least know what you're going to be looking at in a year or two's time. Okay? You won't be looking at, here is the compactification that matches the real world. You're going to be looking at plots of kinematic distributions and counts of this many B jets and that many leptons, and look, there's a feature in this plot and something in that plot, and it means that this particle X indicates the particle Y, Z, and W, and so on. Okay? So the good news, the very, very good news for you guys, is that the 25 years that people have been thinking about what might go beyond the standard model, we have not converged on one specific theory that we all definitely believe in. Unlike the last times CERN turned on in 1983 and discovered the W and the Z that we knew everything about, We don't know everything about what's going on go on at the TeV scale, even though there's some very plausible stories for what it might be. But that means that you're not far behind at all. Okay? Most of the people who have spent their lives thinking about this have spent their lives thinking about 100 models, and if they're lucky, 99 of them will be irrelevant. If they're more likely, 100 of them will be irrelevant. You're not behind, A, and B, the essential ideas that'll be useful early on, because hadron colliders are actually complicated, the essential ideas are really simple. It's kinematics, kinematics, kinematics. Okay, so that's what I'm going to tell you about today. Really simple stuff. This stuff would have been covered in introductory graduate courses in 1979. Okay, it's not so much covered in introductory graduate courses anymore, so I want to go through it so you have some idea of what you'll be dealing with. And a little unusually, let me give you your homework right at the start. So just to give you an idea of the sort of things that you should be thinking about looking at, we've done around here for a number of years now a number of data challenges where somebody makes a model for TeV scale physics, simulates what it would look like at the LHC, and presents the fake data, okay, to everyone else, and everyone else stares at it and tries to figure out what the underlying model was. And we did these exercises with various, as theorists, with various levels of access to the data, just to understand things and practice and so on. But we then did a few exercises like this very recently, where the access we had to the data was almost identical to the access that we'll have, let's say, in the summer conferences of 2009. So experimentalists will try to understand the standard model background. That's going to be their biggest problem. But after they understand the background, they will present what they think of as signals. Okay? So you're going to be staring at what's just signal. And you'll get a bunch of plots. You'll get a bunch of counts and a bunch of plots at the conferences. And then it'll be their job to try to figure out what's going on, and also our job to try to figure out what's going on. There's no sharp demarcation between theorists and experimentalists. If it's a very, very common model, they might figure it out. If it has a little twist in it, then it's up for grabs, and everyone can think about it. But I want to just give you an idea of the sorts of things that are involved. So here's an example that we did where, with the following information, it's actually possible to figure out what the theory is, as was done by a couple of our postdocs here. And this is your homework, okay? So this is a theory. There were something like 500 events of new physics. So it was simulated as if there was 100 inverse picobarn of data at 14 TeV. That corresponds to about a month or two of running after the LHC turns on in March. Okay? 100 inverse picobarn, month or two of running. And there's you don't need to absorb any of this in real time. I just want to give you a visual impression. Okay, so there are like counts. How many leptons are there of very kind? 0, 1, 2, 3, 4. How do they divide up into single leptons? How many jets are there? How many of those jets contain B quarks? How many of them are B jets? What is the correlation between jets and leptons? How many B jets versus leptons? What do the 2 lepton events look like? And then there are a lot of distributions. Here's something, and you'll understand what, if you don't know what they are already, you'll understand what they mean. Effective mass of everything, invariant mass of everything, missing energy, the PT of the hardest jet, invariant mass of leptons and dilepton events, opposite sign leptons, same sign leptons, the invariant masses, invariant mass of hardest 2 B jets. Okay, anyway, that's it. Okay, so however many plots and counts there were, that's the sort of information that you might imagine getting by the summer of 2009. And it is really possible, using extremely simple kinematical ideas, which I will go through, it is really possible to go from this picture back to a supersymmetric Lagrangian, figure out what the spectrum is, what you're seeing, what you're making, how they're decaying, and so on. Okay? So with 500 events, and you can actually do it quite well. So this was actually an easy case. It took our postdocs a couple of days to figure it out. couple of afternoons, not working very hard. There's another case that I'll just show you, which I'll show you because, in fact, none of us have either worked on it or really figured it out. This is made by Jesse Thaler, similar sets of similar kinds of counts, and where'd it go? Oops. Sorry. And another set of plots, okay? Now, these plots actually have a lot more structure because this was done with more data. It was done with about 1 inverse femtobarn of data. So there's all sorts of interesting structure. Anyway, you don't need to pay detailed attention. You see there's lots of two-hump stuff going on in all these distributions. Okay? And Jesse claims that with this information, you can figure everything out, he thinks. And in fact, he left out one plot. And he said that a test of whether we knew what was going on is if we knew which plot to ask for. So anyway, you should feel free to look at both of these after you absorb the very simple kinematical ideas that we go through. And next week, we can discuss them and go through the solutions. Okay. So I can turn this off now. Can we get rid of the screen back there? Thanks. But I want to emphasize it's this kind of plot. It's this sort of, this is going to be the lingo and the jargon and the stuff going on for the first couple of years is going to be about plots like that. It will not be about which precise pattern of, it won't be precision stuff, okay? It'll be basic qualitative things that are aimed at getting us to the zeroth order picture of what is going on. Okay, so let's start then. And I really emphasize this is all extremely basic but important things. What I want you to get out of this lecture and the homework sessions today is an idea of the essential kinematics of a hadron collider, how it differs from what you intuitively expect from Feynman diagrams, and how it very naively expect from staring at Feynman diagrams, and how it differs from life at an E plus E minus collider, why it's so much nicer in many ways. How we go about producing new heavy particles, the properties of the particles that are produced, and also how we go about determining how heavy particles that have been produced decay. Okay? So there's three things: kinematics, production, and decay. Okay? And okay, so let's start off with the very basics. The LHC is a proton-proton collider. The center of mass energy is 14 TeV. I'll throw out other little bits of homework as we go along, if you want to think about them. You may know that the Tevatron is a proton-antiproton collider. You should think about why the heck the people at Fermilab bothered making all these antiprotons. Why would Fermilab be proton-antiproton when the LHCs happen to be proton-proton? Okay, were they just nuts? You know, do they just want to make antimatter for fun? Or is there a reason why Fermilab wanted to collide PP bar? By the end of the lecture, you should be able to figure out the answer to that question. But the LHC is a proton-proton collider. The luminosity is 10 to the 34 per centimeter squared per second, or 10 to the 33 per centimeter squared per second. This is called high luminosity. That's called low luminosity. And what the luminosity means is that if you have a process of cross-section sigma, the number of events per time is just sigma times the luminosity. So that gives you an idea of why the luminosity is chosen to be that particular number. Let me remind you that a TeV scale, as a length scale, one TeV inverse is around 10 to the minus 17 centimeters. Okay? And if we have typical strong interaction cross sections, sigma would be alpha strong squared over a TeV squared at these energies. So this is around 10 to the minus 36 centimeters squared. Okay? So you see that, oh, well, we'll say this again, but these numbers are chosen such that the rates that you get are reasonable human timescale rates. Okay? A 10 to the minus 36 centimeters squared at high luminosity is like an event a minute. Okay, that's pretty good. You know, we can wait minutes. And we can do minutes for months and accumulate lots and lots of events. Okay? Oh, before I do that, let me just, what happens most of the time at the LHC when you collide protons together? I collide two protons together. What happens almost all the time? Does anyone know? They miss. That's why you aim them. Okay, so you aim them, yes. If I take the proton guns pointed at random directions, they miss. But if I aim them square at each other, they don't miss. What happens? Huh? They hit. Yes, thank you. Okay, they hit. So what happens to them after they hit? Huh? Sorry? They, not when you smash them into each other this hard. What happens when they hit? They just smash each other apart, okay? They just completely smash each other apart. The proton is a messy bag made out of quarks and gluons. Okay, we'll talk about this bag in a little more detail. But they mostly just smash themselves up. But, and with what cross-section? How big is a proton? Does anyone know how big is a proton? Okay, that's about how big in centimeters. It's like 10 to the minus 14 centimeters, 10 to the minus 15, 10 to the minus 14 centimeters. So what happens? What happens when they, with that cross-section of order that number squared, 10 to the minus 28 centimeters squared, they just totally bust apart into all sorts of hadrons, pions, crap like that, going down. But that's a gigantic cross-section compared to all of these things. That's an enormous, enormous cross-section. But we don't care. Why? Because exactly, most of the debris of that collision goes down the beamline. Okay, most of it goes in a straight line, back to back, in the direction of the collision. What we're interested in is the short distance collisions. Okay, the short distance collisions are going to be distinguished, just as Rutherford did 100 years ago, by the fact that the scattering takes place at large angles. So by looking at things coming off at large angles, we hope to beat down a lot this essential process. So it's a very, very rare thing. It's going to happen 1 in a million to 1 in a billion times. Okay, it's a very rare thing that we are after. All right. Okay, so let me also give you some of the cross-section jargon. Can you see if I write here? So for historical reasons, 1 centimeter squared is defined to be 10 to the 24 barn. Okay? So we can talk about various cross-sections, millibarns, microbarns, nanobarns. I hate this because I never remember these stupid SI, what like a nano is, for example, or a pico or a femto. I can never remember. But anyway, so this is around the size of the proton, 10 to the minus 27 centimeters squared. Okay? But a pico barn is around this number, 10 to the minus 36 centimeters squared. And a femto is 10 to the minus 39 centimeters squared. Okay? So pico-femto is what the LHC hard processes are interested in. So in fact, the typical cross-section at the LHC, you'll keep hearing the number picobarn, picobarn, picobarn. When we say that by the end of 2008 there will be 10 inverse picobarn, Okay, so you know what kind of, if there's 10 inverse picobarn and the cross sections are around a picobarn, there's 10 events. That's why life is unlikely to be exciting at the end of 2008. Okay, but the kind of integrated luminosities we're talking about for 2009 are an inverse femtobarn. Okay, so that would be 1,000 events if the cross section was of order a picobarn. Okay, and finally, just what I said before, with these typical cross sections with sigma of order a picobarn, we're talking about 1 event per minute at high luminosities. So it's going to be happening at a decent clip. Okay. Now, let's actually, just so you get an idea of the scale of cross sections that we're talking about, the total cross section, which is around this proton size squared, this is around actually 30 millibarn. Doesn't matter. But it gives us something like 10 to the 9 events per second. So about 1 billion events a second. Given how complicated actually storing these events are, it's even impossible to store all of this data. Okay, just even storing all of it is. Now, what about other things? The discovery of the top quark was an experimental tour de force 12 years ago. At the LHC, the top quark is one of the most common things around. Okay? Its cross section is 1,000 picobarn. That means that you'll be making 10 of them every second. Top quark pairs, 10 a second. The cross section for producing a W or a Z from 2 quarks going to a W or a Z is around 10 to the 5 picobarn. So this is around 1,000 a second. For making pairs of W's or Z's and so on, this is around 100 picobarn. It's around 1 a second. So this is why we're not seeing very much of our experimental colleagues these days, and they're working all hours of the day and night. Because what we're interested in are cross sections that look like a picobarn, around an event a minute. And there are things from the standard model that are everywhere from a factor of 100 to 100,000 bigger than that. Okay? And furthermore, these things, you might colloquially have heard things like, well, we can find SUSY because there's missing energy in SUSY, and that's what makes it easy to find. Hogwash. These events have huge amounts of missing energy. For example, every now and then I make a Z. I make a Z at a rate which is 100,000 times bigger than I make anything I'm interested in, including SUSY or whatever. Every now and then the Z decays to a pair of neutrinos. That's missing energy. So there's a factor of 100,000 more events with missing energy just from the standard model than with SUSY. Similarly with top quarks, anything that has a neutrino in it has missing energy. So it's more interesting than that, the reason why we can actually beat down these backgrounds, or what the strategy is for beating down these backgrounds. By the end of the lecture, it'll be clear what that is. And roughly speaking, it's the fact that even though these total cross sections are very big, they die with transverse momentum with a fairly high power. So if you go far out enough and look for hard enough events, they will start being dominated by new physics. Okay? But you'll see that in some quantitative detail by the end of the lecture. But I just wanted to give you an idea of the scales involved. We have to beat things down by factors of 100 to 100,000 in order to be able to extract the signals of interest. Okay. Let me just say a brief word about what we actually see in the detectors. What we actually see are so particles come into the collision and they and maybe we make new particles, whatever we do, they eventually decay down to standard model particles. So what makes it into the detector are, first of all, sufficiently long-lived particles. So of course the electron is stable, the muon is stable on the scale of the detector. Even charged pions and kaons are stable and on the scale of interest. We don't see particles like the pi zero, which decays very quickly to gamma gamma. We don't see, of course, we don't see any of the heavier particles of the standard model directly. So for example, the W decays very rapidly, and the W will decay to 2 quarks, so I'll call that jet. And it'll also decay to a lepton and neutrino, and the branching ratio for this to happen for any given lepton is 10%. So E, mu, and tau. So 30% of the time, so 30% total, it's leptonic. We're going to emphasize leptons because leptons are easier to see than everything else at a hadron collider. So as we go along, we'll talk about that. The Z decays to a QQ bar, and it also decays to F plus, F minus. It does this 3% of the time for each, and to nu, it does this 6% of the time for each. So then the Z is leptonic 10% of the time, invisible 20% of the time, and hadronic the remaining 70% of the time. Okay? The top quark decays to a B and a W, and then the W does what it wants. And how do we actually see these things? Well, I won't go through the details of what the detectors look like, but you've all seen the pictures. All detectors have an onion type cylindrical structure encircling the place where the collision happens. And as you go out, you surround the collision region with different kinds of material. Okay? And the point is that the different kinds of material are going to, particles traveling through the different kinds of material will deposit differing amounts of energy depending on whether they're strongly interacting, charged, and so on. Okay? And that's how we get a handle on the particles that we make. By the way, you've all seen these pictures. These detectors are gigantic. So it's one of the ironies of this business that to probe the smallest distances that we've ever been to, we need the largest detectors. Why do the detectors have to be so large? Does anyone have any idea? Why do we need this? Why do we need these 25-meter diameter things? We need them because someone said it. We need them because precisely to probe the shortest distances, we're going to the highest energies, which means that the particles coming out are also coming out at very high energies. And therefore, to have a chance of studying them, we have to stop them. Okay? In particular, the muons are coming out at these amazing energies of order fuse of TeV. And so you just need these huge layers of material just to stop them. Okay? But anyway, there are, just so you know, there are the various layers of the onion are loosely the tracking chamber, the electromagnetic calorimeter, hadronic calorimeter, and the muon chamber. Okay, and different particles show up in different places here. For example, if I have a photon, it doesn't have charge, so you don't see it in the tracking chamber. You do see it in the electromagnetic calorimeter. You don't see it there, and you don't see it there. And E plus minus does have charge. It does show up in the tracking chamber. It does show up in the electromagnetic calorimeter, not in the hadronic calorimeter, and not in the muons. Pi plus minus, or a proton, shows up in the hadronic calorimeter. A neutron doesn't show up in the tracking chamber, shows up in the hadronic calorimeter. Oh, sorry, these also show up in the tracking chamber. And so on. Okay? So the pattern of checks here covers every possibility, and this is how you figure out what the basically stable particles are that are coming out of the collisions. Okay. So now let's get to business and start talking about the actual kinematics. One of the reasons why hadron colliders are wonderful, it also makes them a little bit more, makes them more complicated, but one shouldn't complain for the kind of gift that you get from the complication. One thing that makes hadron colliders wonderful is the following. Yes?
So there's obviously dangers from misidentification.
Yes. Yes.
What are the biggest dangers?
Well, so I should have, the mis-ID for all of these things is less than the percent level, okay? I should have mentioned, though, thank you. I didn't tell you about some of the other special particles. Thanks a lot, Herman. Which are the B, the tau, and the charm, okay? The B, the tau, and the charm have an intermediate lifetime such that they travel, roughly speaking, hundreds of microns before they decay. There's a range, but between hundreds of microns to a millimeter before they decay. So something something which is done specifically to be able to identify them is to use the so-called silicon trackers, which are even much closer to the beam, at roughly that kind of distance. And what you try to do is identify the displaced vertex. So you make a B quark, okay? You make a B quark, it travels 300 microns and then it decays, okay? You try to see those decay products, you see where they are, okay, in the detector. You try to point them back and see that, in fact, they don't converge to where the beam is. And that's how you figured out that you've made a particle with a long lifetime, and you try to identify it as a B. You can do that, you can try to do that with the B, with the tau, and with the charm. It doesn't work so well with the charm, even though there are some people who are dedicated to doing that. But with the B and the tau, it works pretty well. When I say pretty well, that means that there's, in the experimentalist jargon, there's an efficiency for seeing a B quark if it's really there. And the efficiency for a B quark and for a tau is about 50%. Okay, so is that clear? That means that, if there's actually a B quark there, the algorithm that they have for identifying that it's a B quark will work around half the time. Okay? And for the tau, it's about the same. Maybe anyway, it's about the same. Okay. So now, let's talk about the basic kinematics. So the LHC is proton on proton. Oh, sorry, I didn't finish giving my little preamble. You see, if we collide electrons and positrons, then this is the so-called linear collider. And people love the linear collider because it's so clean and you can control everything and it's antiseptic and so on. But linear colliders are for sissies, okay? One of the problems is that, just to give you an example, let's say there's a resonance somewhere. Let's say there's a new Z particle or something. And it has an energy which is, it has a mass which is 600 GeV. Okay? And your linear collider is at an energy of 1,000 GeV. You're going to miss that resonance. Okay? You're not going to, if you don't hit it right on resonance, that means you'll make it, but you'll miss the resonance. So the problem is that, yes, you can completely control the initial state, and that's also a problem, because you get one initial state. Okay? However, in a proton-proton collider, the proton is just messy bags of quarks and gluons. And so what happens is that every single collision, in every collision, there's something a little different happening. Okay? In collision one, it could be the gluon from this guy and the gluon from this guy, and they smash into each other. And the gluon is moving this fast this way. They're carrying some fraction of the momentum of the proton. Okay? But we get some collision involving gluons with some center of mass energy. Okay? In the next collision, it could be an up quark here and a down quark here. Okay? In another collision, it can be an up quark here and an anti-down quark there, because the proton contains anti-quarks too. We'll talk about that in a second. Okay? But that means every collision is different, and you're scanning over a large range of possibilities. That's the good news. Okay? So that means if there's a resonance there, you're going to hit it on resonance sometime. Okay? The bad news is that this is all happening simultaneously. So the information that we get out, we don't know exactly, we don't control what the initial state is. Okay? We don't even know the center of mass frame that the collision happened in. Okay? Because the gluon here could be moving faster with more energy than the gluon there. So even though we're in the rest frame, in the center of mass frame for the proton-proton collision, we might not be in the center of mass frame for the underlying parton collision. Okay? But that just means that we have to get used to it. It means that doing very, very precise things at hadron colliders is harder. But I want to really emphasize that it's part of the wonderful opportunity that you get for studying physics over the entire range of energies that's accessible, and not just at one center of mass energy at a time. Okay. So this proton has a momentum p, and this proton has a momentum p bar. And I'm going to, so this is, this is the z direction. I'm going to use it, I'm going to find it convenient to work in light cone coordinates. P plus minus is p0 plus or minus pz. And the remaining coordinates I will draw the transverse coordinates p transpose. So just so there's no confusion, a dot b is a half a plus b minus plus a minus b plus minus a transpose dot b transpose. And I will also be working in units for a lot of the day where the center of mass energy is set to 1. Okay? So in these units, this p is 1, 0, 0, 0, and p bar is 0, 1, 0, 0. Okay? So those are the momentum of the protons. But the parton model tells us that we should think of the proton as being made up out of a bunch of partons. And let's say this parton is A, and this parton is B. It's the parton collision that we're interested in that's going to probe short distances, and we're going to have stuff come out of that collision. And the fraction of the momentum of the proton that's carried by the parton is xa. So this guy's momentum is xa, and this guy's momentum is xb times p bar. Now, one of the reasons it's convenient to use these light cone coordinates is that, again, we don't know the center of mass of the collision. Okay? The collision could be taking place at any boost relative to the center of mass frame, but any boost in the z direction. So it's convenient to use coordinates which transform nicely under boosts in the z direction. And that's the whole point of these light-like coordinates. Oh, shoot. Is that they transform nicely under the boosts. Okay. So P plus or minus under a boost goes to e to the plus or minus eta P plus or minus under a z boost. So it's natural to write P plus or minus as some rho e to the plus or minus y. If we do that, then y just goes to y plus eta under z boost. Okay. And this is called the rapidity. Y is called the rapidity. So it just translates under boost, which is the nicest thing it can do. This is really just the analog of polar coordinates. When you have a rotationally invariant system, it's useful to use polar coordinates. When it's Lorentz invariant, it's useful to use these like-cone coordinates. And the rapidity is the analog of the angle. Okay? Now, if we have a particle of mass m, p squared is equal to m squared. So p squared is equal to rho squared minus p transpose squared. And this is equal to m squared. So from here, we conclude that rho is the square root of p transpose squared plus m squared. Okay? This object, which is the square root not of p squared plus m squared, but p transpose squared plus m squared, is called, for obvious reasons, the transverse energy. Okay? It's the energy you would infer that the particle has if all you knew was its transverse momentum. So I will refer to this as ET from now on. And so therefore, p plus or minus is ET e to the plus or minus y. Or if I go back to the original variables, p0 is ET cosh y, pz is ET sinh y. And y is a measure of the angle relative to the beam that the particle is moving in. In fact, if this is a massless particle, or if we say if ET is much larger than m, so we can ignore the mass of the particle, then the ratio of P0 of Pz to P0 is precisely a measure of the angle relative to the z-axis. And there's some formula which involving a log of a cotangent of something. But what you really need to know is that 90 degrees corresponds to a rapidity of 0. Forward is a rapidity that goes to infinity, and backward is a rapidity that goes to minus infinity. And an angle of 10 degrees corresponds to a rapidity of around 3.5. Okay. So experimentalists will use this rapidity variable, to talk about the angle that things are coming off at relative to the beam, and it's a smart variable to use. It's the nice Lorentz invariant. It's a thing that transforms nicely under Lorentz transformations. Z Lorentz transformations, which is useful because we don't know the center of mass frame of the collision in the z direction. Okay, so let's just finish some of these. Finally, in terms of these variables, what is the Lorentz invariant phase space? So one particle phase space is, well, it's d4p delta of p squared minus m squared. That's the phase space. So this is a half dp plus dp minus d squared pt. That's just the d4p. Delta of p plus p minus minus et squared. Sorry, p plus p minus p transpose squared plus m squared. That was just et squared. So if I put p plus minus as rho e to the plus minus y, again, this is just like polar coordinates, so that turns into d. In polar coordinates, there's r dr, which is dr squared. This is d rho squared. D theta in polar coordinates is dy in these coordinates. D squared pt, delta of rho squared minus e transpose squared. So whenever we do the integral over rho, we just go to dy d squared pt. So nothing could be nicer. The one particle phase space is just completely flat in the y and pt variables. It's just dy d squared pt. Okay. So let's just go back to the picture. Now we have these partons. It has XAP. Something happens. We have particles 1, 2, in general, up to n coming out. We had XB P bar. So XAP is just XA 0, 0, 0. XB P bar is 0 XB 0, 0. And the form momenta of everyone else, let me write, I will no longer put the T on E. Every time there's an E here, it's the transverse energy. This is EJ, e to the yj, EJ, e to the negative yj, and P transverse J. All right? So, so conservation of momentum tells us that XA is the sum of EJ e to the yj. XB is the sum of J e to the minus yj. And, of course, the sum of the PTs of everyone is 0. Okay? Now, there's something nice about this, because I told you we don't know what happens event by event. Okay? We don't know what XA and XB are for any given event. We're coming to that in a second. That's the parton model. But if we could see everything about the particles that come out, then we can learn what XA and XB are, just by measuring the rapidities in the center of mass, the rapidities in the transverse energies. Okay? So measuring the rapidities in the transverse energies nails what the x's of the underlying partons were. And we're going to use this over and over again. We're going to convert things that depend on the x's of the partons into things that we can observe made out of the kinematic properties of the particles that come out. Okay? So, for example, the center of mass of the well, that's not an example. The center of mass of the collision is XAP plus XB P bar SAB squared, which is just the 2XAXB P dot P bar, which is just XAXB. So the center of mass is just the product of the two x's. Okay. So now let's talk about the parton model then. And the parton model just tells us that we can't, while we can't predict exactly what the x's are for any given collision, there's a certain probability to find a parton A in the proton carrying momentum fraction xa. So the probability of finding A with momentum fraction between xa and xa plus dxa is f of xa dxa. Okay? Now, we can measure this, for instance, as people did originally, we can measure this so-called PDF from an experiment like deep inelastic scattering, where we take an electron and it collides off the proton. Okay? So it collides off a certain parton in the proton. We don't care about what came out there. Okay, so we can measure it from deep inelastic scattering. It is a quite non-trivial fact, even though textbooks often say it as if it's obvious, but it is not, at least not obvious to me at all. It is a quite non-trivial fact that having extracted these, it is a quite non-trivial fact that in a process-independent way, you can think of the proton as being made out of this bag with a given probability of finding a parton in it. In other words, this probability interpretation works for every process. In other words, that the same PDFs that you extract from deep inelastic scattering can be used for another process where you collide two protons together. Okay? But it is true. It's called factorization, and it wasn't really proved till the late 80s in some famous papers of Collins, Soper, and Sturman. Okay? But it is a true fact. Okay? It is a true fact that having extracted the PDFs from one process, you can now use them for another. Okay? So it isn't circular. Okay? And the fact that it isn't circular is non-trivial. Okay, so let's say, let's then write down what the parton model then instructs us to do. Oh, sorry. Before I tell you that, let's just take a quick look, because it's going to be very important. Let's take a quick look at what these PDFs look like. Okay. In fact, the PDFs depend not just on x, but on the scale where it runs like everything else. There's a logarithmic dependence on the scale of the reaction of interest. So I will show you what they look like. Well, it doesn't matter. What we're interested in is q squares of order of TeV squared. But actually, this log effect isn't too important for what I'm talking about now. Let's take a look at what it looks like. Well, if you're very naive, what would you think that these parton distributions look like? If you're very, very naive, you'd say the proton is made out of 2 up quarks and a down quark, right? So the PDF should be something like 2/3 for U and 1/3 for D. That's what you would think. Okay? That's completely wrong. That is completely wrong, and this is what the PDFs actually look like. See, it's always important to try to guess the dumbest thing first, because then you understand why, when it's not the dumbest thing, you've learned something. Okay, so I'm plotting, for historical reasons, x times f as a function of x. Here's 1. This is a log scale, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and 10 to the 0, 10 to the 1, 10 to the 2. Okay? And it looks like this. This is what it looks like for up quarks and for down quarks. For anti-up quarks and down quarks, looks like this. I won't bother writing down what it looks like for bottom and charm. You can figure that out as another one of your little homeworks. And for gluons, it looks something like this. Okay, well, let me just write down one more of them. Charm looks like this, too. You see a pattern here, okay? So, how do we interpret this picture? First of all, everything goes to 0 at x equals 1. That's because the probability of finding one parton carrying the entire energy of the proton is 0, okay? So it's good they all go to 0 as x goes to 1. The only remnant to the fact that the proton is made out of up quarks and down quarks is the fact that these U and D, oh shoot, the D is bigger than glue 2 for a while, okay? That U and D for relatively large x are the dominant ones. But very quickly, as you go to smaller x, that difference gets washed out. And you notice that as you go to small x, all the quarks, even anti-quarks, all the quarks are the same, and the gluon is something different. That's because there's inside the proton continuously this process of splitting. Okay? I can have a quark go along, and it can split by emitting a gluon and turn into a quark that carries less energy, which can split again. And the gluon can split into a gluon and a gluon and a gluon and a gluon, and so on. Okay? So by this process of fragmentation, as you go to lower and lower energies, even if you thought you started off with only up quarks and down quarks, by the time of the first few fragmentations, all memory of the initial state is gone. Okay? And in fact, these distributions at small x are completely dominated by this fragmentation process. That's why they look identical for all the quarks. And that's also why the gluon has a bigger PDF than the quarks, because the gluon has a bigger color factor. It's a color adjoint rather than a color triplet, like the rest of them. Okay? So, as we'll see in a moment, almost all the collisions that we're interested in the LHC are taking place at relatively small x, less than 0.1 or so. Okay? So that means, as far as LHC collisions are concerned, the LHC is basically a gluon machine. It's a gluon-gluon collider. Okay? That's really what dominates things. And there's a little bit, well, there's some factor of 5 less or so contributions from QQ bar. And that means that there's plenty of anti-quarks in the proton. Okay? So we're interested in the PDFs in this range. Something else that you should notice is that the PDFs here are pretty well approximated by power laws, both for the gluon and for the quarks. Okay? This is going to be useful later. We'll see that this homogeneity is going to lead us to some simple rules of thumb for how things scale, how cross-sections scale with energy, mass, and so on. Okay? But all of those scalings are going to follow essentially from the approximate homogeneity of the PDFs when they start looking universal. Okay? So this is all, everything I said right here is very, very important. So let me just pause and make sure that there are no questions about it. Yes? Yes. Yeah, so maybe we can talk in the discussion section about what some of the error bars on this look like. But indeed, they've been measured at lower energies and they've been extrapolated to high energies because we know their renormalization group equation, which is the so-called Altarelli-Parisi equation. Even if you don't know about the Altarelli-Parisi equation in detail, and shame on you if you don't, but even if you don't know in detail, another little homework for you to think about is, what do you think this picture would look like qualitatively at 10 TeV or at 100 GeV? How does it change with scale? How do you think these pictures change with scale? What does that logarithmic effect look like? Okay. Very good. All right, so now we can proceed. I'm setting these things up. The punchline will be rapid after we understand all these basic things. So. So what the parton model says then is that the differential cross-section for any process is the integral over the momentum fractions xa and xb, the probability of finding A in the proton, the probability of finding B in the proton, times the underlying differential cross-section for the process we're interested in. So if that process has a scattering amplitude m, it's m mod squared over s. The 1 over s is the convention in getting a cross-section out of a scattering amplitude. Okay? So this is the d sigma AB. Okay? Times, well, there's the energy momentum conserving delta function. Times the phase space factor, which is dy1 d squared pt1 up to dyn d squared ptn. Okay, so d sigma is just because I know what xa and xb are from, I know that energy momentum conserving delta function fixes xa and xb. Remember from before, xa is equal to sum of ej e to the yj, xb is ej e to the minus yj. So I can do the integral over xa and xb, and I'm left with fa of xa, fb of xb, m mod squared. And remember, the center of mass energy of the collision was just xa, xb, of ab to 1 to n, times the product of the phase space factors for everybody. Okay? Times the, there's a delta function there, which is just enforcing the sum over PTs. Okay? Where xa and xb here are now not free variables, and they're determined by the formula that we wrote before. Okay, that's the general result. For the particular case of 2 to 2 scattering, which is going to occupy us a lot. Yes? Sorry? Oh, I did the integrals. I did. So sorry, this is what I said. Remember, that energy momentum conserving delta function, one piece was delta of xa minus sum of ej yj. The other piece was delta of xb minus sum of ej e to the minus yj. And then the last piece was the delta function, that delta function. So I used the first two delta functions there to do the xa and the xb integral. And that's why here xa and xb are no longer free variables but are fixed. Okay? All right. So let's do the particular case of 2 to 2 scattering, n equals 2. So in n equals 2, I know that the okay. Then d sigma is fa of xa, fb of xb, m mod squared 1, 2, sorry, ab to 1, 2. XAXB times the rapidity for 1, the rapidity for 2, and the d squared of the pt of one of them. Okay? Because the pt of the second one is just minus the pt of the first one. So I can do the last set of delta function integrals. And I'm just left with 1. Okay. Where, again, xa is just e1 e to the y1 plus e2 e to the y2. xb is e1 e to the minus y1 plus e2 e to the minus y2. All right, so let's talk a little bit more. Oops. Do it here. About a beta 1, 2. Let's so remember S was, let's figure out what were the Mandelstam variables, what are the ST variables for that collision. S is XAXB. This is E1 squared plus E2 squared plus 2 E1 E2 cosh Y2 minus Y1. And T, which is XAP minus P1 squared, I'll just let you work at that as an exercise, is minus PT squared plus E1 E2 e to the Y2 minus Y1. Okay? So something nice to notice here is that S and T only depend on Y2 minus Y1. That had to be because they're Lorentz invariant. Okay? And Lorentz transformations are just a translation on the Y's. Okay? So these only depend on PT and delta Y. Also, if I spin average m mod squared, this only depends on S and T. So that actually motivates us, therefore, in writing that phase space factor, to use variables which are the average of y1 and y2 and the difference of y1 and y2. Okay? So let me use, so d1 y1, dy2, d squared pt is also dy bar d delta y d squared pt. Y bar is a measure of what? Y bar is the average of the two rapidities. So y bar being not equal to 0 means that the center of mass of the collision is boosted relative to the lab frame. Okay? Okay, and now a lot of what's done in this business is to figure out nice ways of writing this, this phase space, which you can use for different reasons. Okay? So delta y and pt, we can trade as independent variables for s and t. We can trade as independent variables for s and pt. And these are nice variables. S and PT are nice variables to trade them for. Because again, these are both very straightforward observables. Okay? This is the S. S, if I saw 1 and 2, I just add up the momenta and I square it. And PT, I just measure the transverse momenta. Okay? Okay, so there's a simple Jacobian. I'll leave it as another exercise for you. So dy bar, d delta y, d squared pt is dy bar, ds, d squared pt, times a Jacobian, which is I'll call this factor J of S and PT. Okay, when the particle masses are the same, there's extra. So let's say the particles 1 and 2 are the same mass, which could be 0. Here we have E1 equals E2, which I'll call just E. XA just becomes root S e to the y bar. XB becomes root S e to the minus y bar. And d sigma becomes dy bar ds d squared pt. This Jacobian, m squared over s of s and pt times fa of root s e to the y bar, fb of root s e to the minus y bar. And this Jacobian, in this case, is just 1 over square root s times s minus 4 pt squared. Yes? 4at squared. Okay. So this is a nice result. All right, now we're nearing the punchline. Can I go 5 minutes over for a minute? I think we started a little late. So I have 15 minutes. Okay. Notice there's something very nice here. The only place y bar enters is in the PDFs. Okay? So the distribution in y bar totally reflects moving around with the same center of mass energy, having a harder gluon from here, a softer gluon from that side, and so on. Okay? So there's a very simple dependence on y bar, which we'll talk about in a second. But if we don't care about y bar, in fact, if all I'm measuring as an experimentalist, if the only variables that I measure are Lorentz invariants, like S, and everything to do with transverse stuff, the transverse momentum, then I would integrate over y bar. For any variable, I would integrate over y bar, and then I have something very nice just as a function of S and PT. Okay? So let me just do that in a second. If we integrate over y bar, then I get d sigma is ds d squared pt j m squared over s, which depends on, again, s and pt, times something which I'll call rho AB, which only depends on S. This rho AB is called the parton luminosity and is just defined as the integral over y bar. Okay, now here are the important points. The fact that we could well approximate, the fact that we could remember for x already at 0.2 or so and lower, we could well approximate the f's by power laws. That means when I take this product, first of all, that means when I take this product that, that naively the y bar dependence cancels. Okay? So the rapidity distribution should naively be flat. In fact, it is flat until you get to the x's where it stops looking like a power law. So in fact, the rapidity distribution is flat up to m over e of order 0.1 or so. Okay? And then it, up to when e to the y bar becomes of order m over e, where the corresponding x starts becoming comparable to 0.1. Okay? But let's forget about the y bar. You should just remember that over a very wide range it's flat. Okay? But it also means that rho AB is approximately a power law. Okay? Rho depends on S as approximately a power, and in fact, that's right. Rho AB approximately goes like 1 over S squared. It's a little different for glue and for UU bar because the PDFs were a little different in detail. But this is very, very, very important. The parton luminosities fall as a high power of energy. Okay? The parton luminosities fall like energy to the fourth, or like 1 over S squared. Okay? Okay. So now let's see how that is reflected in what happens at a Hadron Collider on the production of heavy particles. Okay. So imagine that we have AB is going to some resonance, like it might be a Z or a Z prime or something, and it goes back to 1, 2. And now in everything that follows, I'm going to imagine that 1 and 2 are massless. They're standard model particles. Okay? Just for a second here. Okay? Then we know that m mod squared is well approximated by some kind of Breit-Wigner resonance. So if the mass of the resonance is m, something like that. So let's just call this some constant delta of s minus m squared. Right. Now if I take this formula for d sigma, I can now integrate over s. Okay? Now the only thing that I'm going to measure is the PT of the particles coming out. Okay? So I'm going to integrate over S, and what I get is that d sigma, let me divide by that constant, is d squared PT dy bar, this Jacobian, over m squared, because S is equal to m squared, times FA of m e to the y bar, FB of m e to the minus y bar. Okay, well, let me write this explicitly then. This is dy bar, d squared. Let me work with more dimensionless variables, which are like PT over m. This is the Jacobian. Let me put the dy bar here. Okay, well, you first notice something interesting about this. Notice first that all of the, now really all the y bar, there's nothing else because m is fixed, so all the y bar dependence is in this term, and all the PT dependence is in that term. So in fact, there's a universal shape for what the PT looks like. Okay? And if I plot the number of events as a function of PT squared, then I get something, because of that 1 over square root, that has a square root type divergence at PT is equal to PT squared equals m squared over 4. Okay? This is very useful to look for such a sharp feature. It's called the Jacobean Peak. And it tells you something very nice. It tells you that the PT of the particle coming out is peaked at the mass of the resonance divided by 2. Well, that's what you'd expect, right? You'd expect that its PT can't be bigger than the mass of the particle over 2, but it's peaked at the mass of the particle of 2 with this square root-like singularity. Okay? That's a bit of a detail, but it's nice. I thought I'd say. For the rapidity distribution, on the other hand, it's just what I said before. It's basically flat. Up to where m e to the y bar starts becoming comparable to the E center of mass, which I'd been setting to 1 here, divided by 10 or so. And that 10 was because it was when the x's were around 0.1 that we started getting this approximate power law behavior. Okay? Now, very important. What about the total rate? The sigma total, the total cross-section, goes like 1 over m squared from over there, so I'm just integrating that. Integral dy bar, fa m e to the y bar, fb m e to the minus y bar, which is 1 over m squared rho ab of m squared. Remember, rho went like 1 over s squared, so this goes like about 1 over m to the 6th if it's glue-glue, and 1 over m to the 5.3 if it's UU bar and DD bar. Okay, so after all this stupidity, we start coming to the physics, all right? The cross-sections drop like a crazy power of the mass, okay? It drops like 1 over m to the 6th. This is why and why is it dropping like 1 over m to the 6th? It's dropping 1 over m to the 6th because of the PDFs. Okay? This is why there is such a huge gain when you I'll give the center of mass energy dependence in a second. But anyway, this is something to keep in mind. The production rate for resonances drops like this, roughly between the 5th and 6th power of the mass of the resonance. That's why at the LHC we have to be prepared to cover a very large range of cross-sections. Okay? A factor of around 10 in the mass corresponds to about a factor of 1,000,000 in the rate. Okay? Okay. Now, let's do a slightly more interesting case. Going to see the same physics again over and over. Let's do a slightly more interesting case. Let's do the pair production of heavy particles So let's do AB to 1, 2 with particles of equal mass, m. Okay? Then d sigma, it's always the same formula, is dy bar. And let me work in slightly more dimensionless variables. Just the same thing. Here is the Jacobian factor. I guess I should define these things with hats on them or something. okay? Once again, we can integrate over y bar. To get d sigma is d squared pt over m ds over m squared over root s over m squared s over m squared minus 4 et squared over m squared m mod squared over s over m squared, rho AB. Okay, very important point. All of these things are falling with s. Okay? Rho AB is falling like 1 over s squared. There's a 1 over s there. No amplitude in the world has an m mod squared that we care about, has an m mod squared that grows faster than s cubed downstairs. Okay? If it does, it's incredibly small amplitude. So every field theory amplitude that we know will die. Every single one of these things dies with s. S can't be less than 4 et squared, however. Okay? That's just that's the singularity of the square root down here. But that means something, that means that all of this is dominated for s as close to 4 et squared as possible. For exactly the same reason, they're also dominated by the smallest pt that you can have. Okay? All, again, I stress all because of the rapidly falling parton luminosities. This is dominated by the smallest s and the smallest pt. Okay? So the punchline, very important, is that the heavy particles are primarily produced at rest, produced at threshold. Okay? I can have a 10 TeV collider, and if I'm making top quarks, TT bar, you might think naively, well, I have proton, goes, the center mass energy is 100 TeV, let's say, even 14 TeV. You would think the top quarks are whizzing out. Right, carrying, like a TeV each. No, the top quarks are almost basically made at threshold. Why is that? It's because even as you crank up the energy, it pays, and in fact, you just slide down the x that you need. You need lower and lower parton energies to make the particles, and that's great because you're getting rewarded by a much bigger PDF. So no matter what the energy is, the heavy particles are essentially made at rest. Okay? Yes? Yes. Yes.
It means that there are a couple, like 1,000 Spartans.
Yes. That's right, exactly. So that's why you're winning. The gain in the number of partons is so large that it always pays to make the new physics at rest. Okay? This is incredibly useful. This is an incredibly useful fact because, anyway, it's useful for many reasons, but it's also a big qualitative fact about hadron colliders, which is very different than an E plus E minus collider. Let me, in fact, tell you, let me be a little bit more specific. So as an exercise that you can do, just taking this distribution and putting in the power laws for rho that I told you, just to get it more quantitatively, what do I mean? the expectation value of PT divided by the mass, which is a measure of the boost, is around 1/3 for glue and 1/2 for UU bar. And the expectation value of S is between 5 to 6 m squared for UU bar and glue bar and glue versus 4m squared, which is strict threshold. Okay? So that gives you a measure, a nice measure of how boosted things come out. They're not at rest. They have betas that are like the square root of 1/3 or 1/2. Okay? Independent of m. It's another nice thing. So any mass particle, more or less, comes out with the same typical beta. Okay? And the PT is around 1/√3 or 1/√2. Okay. So let me just, I can finish up with just with 5 minutes then. The fact that new particles are created at threshold and this rapid parton luminosity fall-off are responsible for a very big qualitative difference between production at hadron colliders and at E plus E minus colliders. Let's say you have an E plus E minus collider and you want to make some new particle. Okay? If you go to very high energies, the cross-section just drops off like 1/center of mass energy squared. Okay? So if I have some new particle, E plus E minus, and I want to make XX bar, the cross-section just goes like alpha squared over E center of mass squared. Nothing I can do about it. Okay? It goes down with increasing center of mass energy. That's why you have to go to much higher luminosities at a hadron collider to make up for it. Okay? But by contrast, at a proton-proton collider, the cross-section goes up with center of mass energy. The cross-section for producing some massive particle X goes up with center of mass energy. In fact, sigma should go like, because it's being made at rest, it's 1/m squared, but we get to win that parton luminosity factor, which scaled like the 4th power roughly. So this gives me something that goes like E center of mass to the 4th for glue, and E center of mass to the 3.3 for QQ bar mediated processes. Okay? So if you look at the plots for the W production, TT bar, everything, at the LHC, they're way bigger than at the tevatron. Not because it has much more center of mass energy. In fact, that would go the other way. But because of this fact that the particles are produced at threshold, and if you go to much higher energies, you get to live off the many, many, many more partons that you have with the appropriate energy to make them at threshold. This also explains why there is such a jump from going from the tevatron to the LHC. It's those big powers. Okay, a factor of 7 in energy not only gives you access to new particles, it gives you this 7 to the 4th increase in the cross-section relative to what you had before. That's why if we take a 300 GeV gluino, a 300 GeV gluino is about the limit that's being set by the tevatron today. But when the LHC turns on at full luminosity, you will pair produce 300 GeV gluinos every second. Okay? So you go from never having seen them to making 1 a second, which is the particle physics definition of a factory. Okay? And so finally, all of these power laws also help us understand very basic overall cross-sections for new physics. So let's say we're talking about Susie. Then as a function of the mass of the superparticles, this is around 10 to the 3 picobarn, around a picobarn, and a femtobarn, which is 10 to the minus 3. Then we just get plots starting at 200 GeV and going up all the 2 TeV. We get things that span we get plots that look like this. This is for strongly interacting things, gluinos, squarks, and so on. This is for weakly interacting things, leptons, neutralinos, and so on. This is for direct production, So you see that the cross-sections span, as I said before, about a factor of order 1,000,000. Okay? The typical cross-section is around a picobarn. It could be bigger by a factor of 1,000 or smaller by a factor of 1,000. Okay? And for the weakly interacting stuff, this is about a factor of 1,000 smaller. And you should do as an exercise, try to understand where that factor comes from. One factor is there's an n color, which is not a too big deal. There's an alpha strong over alpha weak squared factor, which buys you a little bit, and which buys you about a factor of 30. And there's the fact that the colored guys get to be produced from the gluon PDF, whereas the electroweak guys coming from W and Z production have to live off the Quark PDFs, and are then down by another factor of 5. So putting all those things together gets you about a factor of 300 to 1,000. Okay? But this tells you something, also very important, that the LHC will make colored particles up to, let's say, 5 TeV eventually, but uncolored up to maybe 300 GeV. Big difference for direct production. Okay? Of course, we can get the uncolored particles in decays of the colored ones down the line, which we'll talk about later. But for direct production, the LHC really is a gluon machine dominantly. The colored things are made much more frequently than the uncolored ones. There is about a factor of 1,000,000 in range of cross sections, but it can go up to around 5 TeV for colored guys, around 300 GeV for uncolored guys. One of the motivations many of you have heard for new physics at the LHC is dark matter, right? Dark matter may or may not be directly produced. We could have dark matter lighter than 300 GeV. We could have dark matter at 2 TeV. Okay? And if it's at 2 TeV, we will not produce it directly at the LHC. We can still get it indirectly. It's possible we can get it through the decays of other particles, but direct production will not happen. Finally, all of this tells you why it is that most of the excitement of the LHC is in the first few years. Because the really big gain is the jump in energy, which gives you all those big powers. Okay? After that, accumulating luminosity, buys you fractional powers relative to what you bought from the first big jump. That's why you hear people say, if SUSY's at 1 TeV, we'll discover it in the first 2 months. Okay? But if SUSY is at 3 TeV, 2020, maybe. Where is this big difference between 3 TeV and 1 TeV coming from? It's called 3 to the 6th. Okay? That's why there's such a huge difference. So the excitement at a Hadron Collider, at any collider, but really at a Hadron Collider, is really front-loaded at the beginning. Okay? If there's new stuff, we're going to see it. We're going to see it quickly. Figuring out what it is the goal of my remaining lectures, and talking about how these particles decay is the goal of my remaining lectures. But what I want you to take away from here are the essential lessons. New physics is produced essentially at threshold. The production cross-sections drop with very high powers of the energy. We have to be prepared to encounter, even for new physics, cross-sections that can differ by factors of order 1,000,000 in the LHC energy range. And on top of all of this, of course, there are standard model backgrounds, which are anywhere from 100 to 100,000 times bigger than the signal that we're looking for, that has to be dug out. Okay, that's all.